purpose of today's lab is we're going to look at the phenomena and concepts involved in static electricity. There are three main methods of static charging, including friction, rub two things together, contact, touching, and then induction is the tricky one. Okay? You'll try that. And then looking at how Coulomb's law works here. There are going to be 5 stations you'll rotate around the room to try out. And then as a bonus, I'll have the little static fly stick out. You can try it out. It's kind of cool. And there'll be some things that I'll just tell you guys to try out just because it's really cool. That's all. Okay? So the first one is called magic wands, dancing fur, and magic cans. You're going to charge up a white PVC strip by friction using fur. Okay? So instead of strips, we got a nice plastic pipe because it's strong and then it's bigger. And plastics like to do what to electrons? They like to grab them. Okay? They have a high, what we call electronegativity from their atomic structure. What do you know about furry, woolly, fleecy kind of things? They like to give away electrons. Okay? So what you do is you pick two things on purpose that are opposite of each other. Okay? It's on what's called the triboelectric series here. And this is called charging by friction, where literally two things rub together. Okay? And if you listen carefully, you can even kind of hear that snap, crackle, pop there, right? Okay? And now, what do you know about opposite? Opposite charges will attract. So if you look at the fur carefully here, it's actually being attracted to the wand there. You see that? And if you look at the station over there, okay, I actually put out some little tiny pieces of fur. So in other words, another thing you could do then to prove that these are oppositely charged, and by the way, you can't see the charges, right? It's all invisible to the human eye. It's so small. But you should be able to see that fur like dance through, and there we go, and attract against the force of gravity. You can actually get it to levitate. Levioso. See that? Okay, kind of cool, right? 666. There we go. Mr. Lau sold his soul to the devil. No, not at all. Okay, it's just simple electrostatic force there. Okay? So anyway, grabbing the sink again to ground myself there. Picture's worth the what? 1,000 words. Okay, so let's draw what happens. Here we have the plastic pipe. Here we have a piece of fur. Okay, there we go. When I rub the two together, the plastic likes to grab electrons. Okay, so one little thing I realized people were confused by is they're like, well, Mr. Lau, does that mean there's no positive charges in the pipe? No, not at all. It's just it has an excess of electrons, right? Therefore, it'll have what kind of net charge? A negative charge. So what I want you to do is draw on some extra electrons on here. Negative charges. Let's say we draw on 6 to represent an extra 6 trillion electrons. That's all. Okay? Does that mean that there's no positive charges? No, not at all. It's just that there's a net charge. What's the net charge on the plastic strip there? It'll be what? Negative, right? Because it has an extra 6 trillion electrons. Okay? How about the fur? What did the fur do? It what? It gave away electrons, didn't it? Therefore, it's going to have a net positive charge, isn't it? So what we want to do is we want to illustrate the conservation of charge by drawing on, if we drew 6 charges here, we should draw 6 here to represent the fact that we did not create or destroy charge, we just transferred electrons from one charge to another. That's all. Okay? So if there are 6 trillion negative excess charges on the plastic strip, there'll be a deficiency of electrons on the fur. So it'll have a net positive charge of 6 trillion protons. You see that? And what we want to show then is we were able to prove that by drawing in these force vector arrows. What's that? It's an arrow that represents the force between two objects. So what do you know about opposite charges? They will attract. So these are force vector arrows. It's F for force, representing the force. Let me zoom in a little bit here. Between the charges there, okay? And according to Coulomb's law, the amount of electrostatic force, we're not really worried about all the crazy math. F equals K, the electrical constant, times Q1, Q2, the charge on each object, over the distance squared. It's the idea that if you have more charge, there's more force, but then the other factor is what? Distance, right? So if you get further away, the distance drops off to the inverse square. So if you're twice as far away, it's not twice as weak, it's 4 times weaker. So make these arrows for the further charges smaller to represent that idea. You see that? Okay? And you're like, wow, this is really silly. I don't get it. We're just drawing a lot of minuses and pluses and little arrows and all that. And what we're trying to get you to do is to not focus on just doing all this crazy math. Because we could shove in a bunch of numbers and plug and chug. But it's getting those basic ideas down. Because this is what makes modern life so cool. Okay? I mean, normally you don't try to like run a comb through your hair and pick up a piece of fur or whatever. But do you take a picture with a digital camera? Do you write an English paper and store it in your digital static memory on your computer? Yeah, things like that, okay? We're going to do one more, okay, to give you the basic idea, and then we're going to set you guys loose. Now we're going to try to roll an aluminum soda can across the table here, Okay? And actually, we're going to do the opposite. Instead of drawing it first, I'm going to do it, and then we'll see if we can work backwards and picture it here. Okay? So I'm just going to see if my webcam will pick this up for later here, hopefully. There we go, close enough. True or false? An aluminum can has no charge in it. Which one? True or false? That's false, right? An aluminum can definitely will have charges in it. So anyway, I can get this thing to be attracted to my charged object, right? Without even, do I have to touch the can? You guys remember? No. I don't, okay? And here's why. The can has no net charge. It's neutral. If it has 50 billion protons, it also has what? 50 billion electrons. But I can get the can to be attracted to my negatively charged rod. And here's why. As I bring this closer, if I want more force of attraction, what do I want to do? Put on more what? More charge. The other factor is what? Distance, right? So if I move this twice as close, there's twice as much force. 4 times closer, 16 times, 10 times, 100, right? But all it is what can be attracted by the negative rod here? The what? What kind of charges? The positive charges will be sucked closer in the can. The negative charges will be pushed what? Further away. So because the overall force of attraction will be stronger than the force of repulsion, okay, you can actually move the can without touching it. Okay, so during Thanksgiving dinner, you could like freak out your friends and family, right? You sold yourself to the devil, 666. Ah, red devils. Levioso. Okay, whatever, right? So, what's going on? What the heck's going on? Let's try to picture this. Picture's worth of what? 1,000 words, okay? And the devil is really in the details, okay? So, let's draw out the aluminum can on the table. And again, did we actually touch the can with the rod? No. We didn't. So what's the net charge on the can? Is it positively or negatively charged? Or is it 0? Which one? It's a big fat what? Big fat 0. Okay? So hang in there. Okay, guys? Why does the can move? Let's see if your brain works, okay? Because we put on an excess of negative charges here. Let's say we have 6 trillion electrons. What can the electrons in the rod do to the electrons in the can? It will attract them or repel them. It will repel them to the far side of the can. I'm going to take my pencil here and do a dotted line to show that the can gets what we call polarized. Maybe label that really quick, okay? Remember how we polarize light by separating it with a filter? You can polarize things electrically by separating the charges. That's a really important idea in nature and in technology. So remember the little e-ink video clip? I thought it was really cool how they showed that if you have a little ink capsule, if you electrify it and then you can either attract or repel, you get either the black or the white ink to reflect the light through a red, green, blue filter. It's like really cool. It's like just real simple. And it works, okay? So what can be attracted then to the near side of the can? The what? The positive charges. And again, if I draw 3 on this side, I should draw 3 on that other side, just to show that whole conservation of charge idea, okay? Then, what do you know about opposite charges? Opposites will what? Attract. So draw these force arrows showing big time attraction, okay? F is for force. And then how about the negative charges? They will be what to each other? They will be repelled, okay? And notice the overall force of attraction will be stronger than the force of repulsion. I make these arrows tiny, okay? A tiny little force versus these bigger forces over here because these negative and positive charges are closer. So the net charge on the strip is negative, but I can still attract that polarized can there. Okay? So in today's lab, you're going to try out a couple different stations here. And what's kind of cool is when we do a computer lab tomorrow, it's going to help you visualize what's happening in an abstract manner. Okay? And it'll make a lot more sense because you've done it for real around the room here. Okay? So let me just give you a few tips on our last station so you can see what's going on. So try the pith ball station. It looks like it's attracted, then repelled, and that can be confusing if you don't try to visualize what's going on with the charges. So here's a little trick. Tomorrow you're going to do this little computer visualization that helps you picture the charges. But by doing it in real life first, it's going to make a lot more sense, okay? So notice that when I bring this charge rod closer, this pith ball isn't actually charged up. It's got 1, 2, 3, 4, 5 positive charges, 1, 2, 3, 4, 5 negative charges. There is no net charge. But I can attract it because I polarize the charges. The overall force of attraction is greater than repulsion. But once I touch it, remember what happened in real life? What did the pith ball do? It shot away. You see that? Because now the extra electrons go onto the pith ball, and it's got a negative charge. Picture's worth